Now here's a bit more nomenclature to deal with a potential complication in using wires that can be broken or backed up. So let's imagine our 3-channel wire. And it's got the usual configurations for the PC and the CC and the break lines. And let's suppose that our break wire was set up to bring us back to this point. So to restore the head of the wire to this location. So we build our PC and our CC, and remember each of these has a feedback signal going down to the south. And each of the program channel cells routes that feedback into the previous stage's control channel. And there's other circuitry over here, which I'm not going to draw again, but that's the 2 AND gates controlling the distribution of the CC line. And so right now with this setup, our target cell is over here. So that's our target. And when we assert the break line, we clear this configuration out. We load this truth table with 0. And in doing that, we cease sending a 1 down into this. We stop sending a 1 into this cell's eastern input, which means that this is now taking the CC input and feeding that into the PC's northern southern input, northern output of the CC. So this is ultimately driving a 1 into here, which is going into the control input. So after asserting the break line, these become the head cells, and this is the new target cell up here. But consider what happens if we go ahead and we start to extend this wire again. We're going to configure this cell to configure this one. That's fine. This is already configured. And then we're going to go ahead and we're going to build our usual circuit in here. So we're going to take the 1 and send it out to the south. And we're going to take data from here, send it to control, and route data east and west. As soon as we do that, this 1 coming down here being fed back says this is no longer the head of the wire. But in fact, this is not the head of the wire either, because this cell here is still sending a 1 out, and that's being fed back, and that's telling this that it's not the head. And in fact, as soon as we reprogram this 1 cell, our wire is completely restored, and this becomes the new target cell. So we've broken the wire and moved the target from here back to here, but if we rebuild this single cell, our whole wire restores itself. And that's not usually what we want. Usually what we want is we want to be able to begin extending the wire 1 step at a time, because a lot of times what we're trying to do is, such as in this case, break the wire and then extend it not quite as far as we did before. So we need a way to make sure that as we program this new PC cell, that it doesn't cause the whole wire to kind of rematerialize. So we need to do what's called a pre-clearing sequence. And that just adds another 2 steps to our configuration program. And it looks basically like this. And I'm just going to show a 2-channel wire here. If you have a break line, which you probably would, then you need to take those steps into account also. So here's our program channel, here's our control channel, here's the head of the wire, here's our target. And here's the program that we're going to use. So step 1, I'm going to set my control channel equal to 1. And my program channel is going to be set up a little differently from before. It's going to put a 1 into the control input on the south. It's going to take data from the west and route that to the south. But it's also going to put a 1 into the control input on the east. And it's going to put a 0 into that cell's data input. Okay, so what have we done? Step 1, we've programmed our target, and we've given it basically this configuration. In step 2, we set the control channel to 0, and we set the program channel equal to our usual CC cell. And so in step 2, we're programming this cell, and that's going to achieve its final configuration. But also in step 2, because we've set CC to 0, this cell, the target, is in data mode, which means it can assert its C output not only to this cell, but this C output to the east will put this cell into C mode. So this is actually being configured in step 2 as well. And in particular, its truth table is being loaded with all zeros. So to indicate that we're simply clearing this, we put the 2 in parentheses. So we're configuring it, but we're not actually loading a particular truth table into it. We're just configuring it for the sake of clearing out its truth table. And then in step 3, again, CC equals 1, PC equals whatever our usual PC head cell is. So put a 1 to the south for the feedback, take the data from the south, feed that to the control input on the east, and copy the data between east and west. And so in step 3, we program this cell again. That becomes its final configuration. And then step 4 is the quiescent period. CC equals 0, PC equals 0. So at this point, it does not add 2 extra steps, but it does something extra during the configuration process. What happens is during the second step, we pre-clear this cell that's going to become the new target cell. When we do that, we get rid of the fact that this was putting a 1 into its southern output. So now, after we finished programming this in step 3 and we've returned it to D mode, this will be our new target cell, but it will no longer be putting out that 1, which would normally cause a feedback into this CC head cell and cause the whole wire to extend. So this allows us to make a wire and then break it at some point, and then go ahead and start extending it one step at a time without it having this property that as soon as we restore that missing cell, the whole wire reappears. So we simply clear one spot ahead of us as we're moving through. So that's another 4-step sequence, but it's got this pre-clear step to it. And again, when we put the step number in parentheses, it means that we're clearing the truth table at that step. So now we're starting to build up a repertoire of different ways that we can annotate what's happening during the steps of these sequences. And we can define sequences for a number of basic operations. We can do wire extensions like this, wire extensions with a break line. We can actually do a break line with the CC and PC reversed. That's a little more complex, but it is doable. And the next one that I want to talk about is a 12-step sequence for making a corner. So moving a wire from, say, west to east, and then at some point making a turn so that you start extending down to the south. That's obviously going to be a very useful sequence, and that will be a good illustration of how we annotate these kinds of operations. From there, we're going to start talking about putting collections of sequences together. So a sequence of sequences is something we call a supersequence, and supersequence generation and analysis is really the key to understanding how to use the cell matrix and how to take full advantage of its self-configuring capabilities. That'll get us into bootstrapping, it'll get us into Medusa circuits, and ultimately into supercells and all the other dynamic behaviors that we're interested in on a cell matrix.